It's lunch, but I couldn't help but want to add this footnote. Guys, do you mind? Okay. Okay, so I couldn't wait until tomorrow to add this footnote, but this is just a footnote for our, I think, 8th or 7th lecture on the F manifold. But the thing is, I just got the idea now, and I want to introduce 4 more types of toruses or donuts, femboy donuts, to the study. So, I suppose I want to start with the simplest one, which is a toroidal polyhedron. So, a toroidal polyhedron. These are a class of polyhedrons that are 3D shapes that look like a torus. So I'll try to draw one here if I can do that. So the one over here, that, I think that's it. Okay, one more. And inwards in there. Okay, and then goes like this, and then like that. So like there, next, it's there, and then we're gonna add some sides like that. Okay, so this is an example of what is an F, or what we call the F T2, T3. T2 because this is a surface, a two-dimensional manifold, and T3. Okay, so in general, characters are called toroidal polyhedrons, or abbreviate them as, or rather the femboy version of these guys, F, T, T2, Pn. Actually, this is P0 or P1 because it's a genus 1 torus. And genus 1 toruses have only one pole on them. But in general, if you have some genus N torus or toroidal polyhedron, we use to the N. We use the abbreviation T to the N, or FT2 to the Pn, or just times Pn. And one thing that we want to discuss about when we're talking about polyhedrons is their Euler characteristic. So the Euler characteristic is some number or some invariant that doesn't change when we try to morph the shape itself, right? So for a cube, so the Euler characteristic is always 0. So V, it's given by this formula, V minus E plus F. Very simple. Equals 0. So all 3-dimensional polyhedrons have an Euler characteristic of 0. So the vertices minus subtracted by the edges and the faces is always 0 for all 3-dimensional polyhedrons or polytopes. So a cube's, let's say we have a cube here. A very simple polytope. So we know it has 1, 2, 3, 4, 5, 6, 7, 8 vertices. And then it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12 edges. And then it has how many faces? 6 faces. So yeah, this is a 12 minus 12, 0. Actually, no. That's wrong. Get this. Let's recount that again. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, and then times 6 is. this cube's Euler characteristic is not 0. Maybe you guys can tell me in the comments below why it's not. Even though we know it's supposed to be 0. So that's a small discrepancy right there. So that's for genus 1. So for the genus 1 toroidal polyhedrons or F toroidal polyhedrons, it's always gonna be 0 also. It has to be 0 also. So for this polyhedron over here, this FT2P1, its Euler characteristic must be 0. But we also want to consider the Euler characteristic of N genus. So the genus is, it doesn't have only one hole but multiple holes, N holes. So if we consider our toroidal polyhedron that has N holes in it, its Euler characteristic, which I think it's denoted by chi, of F(P2)Pn is equal to 2 minus 2n, where n is the amount of holes. Actually, n is the amount. This small n here is the amount of shapes in it. So for this FT2P1, it's actually P3 because we have 3 shapes. We have this quadrilateral over here, this quadrilateral over here, and then this bottom quadrilateral over here. God, those guys are tongue twister. Alright. And so this is our genus, the amount of holes we have here, and this is the amount of shapes that we use to form the polyhedron. So once it looks like a donut, then it's a toroidal polyhedron. Okay? And it's made of solid stuff, but that's that. Okay, so this is the second type. The second type of our Femboy manifold, or Femboy donut. Can't just have one, can we? Okay, so the second one is actually an alternate definition of our first definition for the Femboy donut. So our original definition for FT2 is a Cartesian product between two FS1s. So Femboy circles. So FS1 cross FS1. And such that these FS1s are elements of our universal Femboy underlying set. So that's that. It's just a shortened version, but just check the original lecture for the full description or full atlas. So this is a shortened atlas for this manifold. Okay, so that's that. But there's an alternate definition which I will call FT2 alt, ALT, and it's defined through this atlas. X square root of fx squared plus fy squared minus 1 squared plus fz squared equals 1/4, such that these three variables rather, fx, fy, and fz are part of the free product of f. Okay. So what we have here is, well, it's an alternate definition of, or alternate atlas at least, for our FT2. So yeah, another definition here. And I think it's based on the fact that instead of measuring the radii of the two circles with respect to the origin, we're measuring the radii with respect to some unit circle. So yeah, this is the alternate definition for our FT2. And so next, the third one, our third definition, our third version of our FT2 is actually a flat version, a flat projection called just FT. And T is just a flat torus. That's why it's just T1. It's a curve rather, not a surface. But it still, in a way, encapsulates what T2 looks like. So if T2 is a regular torus or donut, if this is T2, then a regular D is probably just something like this. Or just a circle or top-down view of it. So FD, FD now is just more. It's a more compact and easier to understand definition of our Femboy donut. So now Ft is defined by the atlas x squared plus y squared equals 1/2, and then another extra rule. So we have two other variables, x and w, not omega, but w, whose the sum of their squares are also equal to 1/2. And then such that, well, these guys are part of S3, or F3. So, okay, I want to change the variables. I forgot to change the variables in my notes. Okay, so these guys are F, these are families, not really variables. Fy, Fz, Fw. Well, such that these guys, I'll just do dot 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 because it's a waste of ink, are elements of the S3, Fs3. So this time, instead of this product of 2, so S2 is the product between, the Cartesian product between two circles. So this one over here is some, you can say some solid shell, or a surface, or a three-dimensional shell, a spherical shell basically. So now S3 is some four-dimensional hypersphere, I believe, or hypershell. So it's just the product of 1 3 times, obviously. But this time here we have some, we're sort of making a Femboy extension on it. So it's some F. So now it's just the product of F S1 with it itself three times. Okay, so that's this is the flat FT. So flat Femboy donut. So the last one, this one's going to be a bit of a doozy. We need to first talk about Femboy polynomials. Okay, so what's a Femboy polynomial first? So it's basically just, if we treated f as some variable, so like x, basically replace x with f. And instead, we want to construct some space, which is, say, which I like to call phi of f, and then f. Okay, let's construct this space. So how do we characterize a curve like this? Well, of course, it's basically just phi of f. That's that. This is the y coordinate, this is the x coordinate. So, okay, what if we grab our regular torus, ft2, and have some cubic polynomial and then embed it inside or on the surface of that torus? So given the torus, right, given the donut, what we want to do is...
Hello, miss. Magbibigay lang ng departure permit.
Okay, thank you.
Alam ka na ng class, no? Naglanan.
It's okay, please. Okay, so when we were torus, what we want to do with that curve, what if we want to sort of embed it on the surface? So what we want to do is, given some torus or donut, we literally put it on the surface, right? We embed it on the surface. Okay, let me just pause this. Okay, now that the commotion has died down a bit, I wrote it down here. This is the atlas, at least, for the embedding, or rather just literally putting it on the surface of a given f polynomial or curve on the surface of our Femboy donut. So the key feature of this embedding that we're doing is that the roots of this polynomial are on the boundary of the donut. So if we have our donut, the part wherein it ends, or the side where it ends, so I'm going to write it here. So if we take a top-down view, we have two boundaries on a donut, so the inside and the outside. So the key feature of this embedding is that the roots, well, let's say one root, phi of 0, this is phi, not f, sorry. phi 0 lies on the boundary. It lies here, or let's say another root. So phi not 2. Let's say if it lies there, it should lie there. That's one key feature of this. So you know that this is the boundary of our given donut, right? So what this is saying is that the roots are on the boundary. They're literally on the boundary over there. They're not here, they're not inside here, but they're on the line. That stops it, it stops the points. So this is actually one of the most interesting ones because it's not really a type of donut per se, but rather it's a sort of action that we're doing. It's some, well, it is a type, but it's not exactly a version of it, but rather a sort of thing we're doing on it, and then we're obtaining some new entity, right? So that's actually it for this footnote. I know this footnote's a bit long, and yeah, 16 minutes long, and it takes some time to understand because this is a literal polynomial. Another note is that this polynomial must be of degree 3, so it's some cubic polynomial. That's one way of saying, or one way of making it such that its roots are on the boundary. Or it could be something like a trigonometric function, like sine or cosine, or its polynomial expansion or Taylor expansion. So that's it for this footnote.